Hello students, welcome to this lecture. In last lecture we discussed about the basis sets. Before that we talked about how we can do Hartree-Fock calculations. So together with the implementation of the basis set and the knowledge about Hartree-Fock calculation, we are now in a position where we can treat large multi-electron atoms or molecules and solve their the Schrodinger equation corresponding to them within Hartree-Fock formalism. One thing that we notice is that even if we realize that if we take better and better basis functions, we can reproduce the molecular properties in a better way. But it is clear that even if we take the best of the best basis function, it would still not take us. Of course, it will make our calculations much better, the quantities that we will be getting perhaps would be better, but it can take us only to one extent, not beyond. That is because we have still some problems with the approximations in the Hartree-Fock formulation itself that limits the accuracy of these calculations. In this lecture, we will discuss some methods or some ways as to how we can go beyond this Hartree-Fock method, the so called post Hartree-Fock methods, and obtain the electron correlation that is still missing in this Hartree-Fock method. After we complete our Hartree-Fock calculations, we would obtain this set of spin orbitals. So, if we take k number of basis functions, we would construct k number of molecular orbitals. Now, this k number of molecular orbitals correspond to 2k number of spin orbitals. So, once we have completed our Hartree-Fock calculations, essentially we have this 2k number of spin orbitals available to us. Now, for a molecular system, we have, let us say, n number of electrons. So, what we do? We simply occupy the lowest n number of spin orbitals with electrons. So, this is what we do. Suppose we have n number of electrons and we go from the lowest energy orbital to nth spin orbital and populate those orbitals with electron. That leaves us with 2k minus n number of orbitals, which are so called virtual orbitals. So, therefore, after Hartree-Fock calculation, we have n number of occupied orbitals and 2k minus n number of virtual orbitals. The Hartree-Fock wave function we wrote down as a Slater determinant, where the lowest n orbitals are occupied with electrons. We do not talk about the rest of the spin orbitals because the electrons are not there. Now, imagine, so this is one n electron wave function for the molecule. Of course, this wave function corresponds to lowest energy, that is all right, but I can also imagine that if I take one of this electron, suppose this electron, and put it suppose in chi p, the p spin orbital. In that case, what would happen? It will also give me another molecular function, n electron function, that I can represent in terms of a Slater determinant, which is shown as here. Here all other spin orbitals remain same, except for the fact that the electron I from chi a spin orbital has gone to chi p. Now, this new Slater determinant I am representing as phi a p. So, that means electron has gone from a to p spin orbital. And similarly, I can also imagine that if I take two electrons, that means the electron at chi a and electron at chi b, electron at chi a goes to p and electron at b spin orbital, let us say it goes to q. In that case, I have this another Slater determinant where electron I and j have moved from a and b to p and q. So, now this Slater determinant is given as phi a, b, p, q. So, these are the places where the electrons have changed their position corresponding to the Hartree-Fock wave function. So, Hartree-Fock wave function is nothing but one of these molecular n electronic basis function, but I can also construct many other n electron basis functions from the same set of spin orbitals that I got after solving Hartree-Fock equations. Now, all these wave functions are molecular wave functions representing that particular n electronic system. Of course, I have got one ground state or the lowest energy state, that is the Hartree-Fock configuration, where I have occupied all n electrons in the lowest n number of spin orbitals. But if I carry out all this single excitation, one electron excitation, you can imagine that I can have this many one electron excitation, because I have got, let us say I pick any one electron and I want to put in one of these 2k minus n virtual orbitals. So, therefore, I can do that in 2k minus n number of ways by picking any random electron, but I have n such electrons. So, therefore, the total number of one electron excitation is that 2k minus n, multiply that with n. Now, similarly, I can do this many number of 2 electron excitation. I can randomly pick any 2 electrons, and the number of possible ways I can do that is given as n into n minus 1 divided by 2, and I can take these 2 electrons and put them in the 2k minus n virtual orbitals, and number of ways that I can do that is given by this 2k minus n multiplied by 2k minus n minus 1 divided by 2. Now, similarly, I can talk about 3 electron, 4 electron. So, if I want to generalize that, if I want to do m electron excitation, I can select any m electrons from the set of n in this many ways. So, this is this n m is essentially the binomial coefficient n m. So, n m number of ways I can pick m number of electrons from this set of n electrons, and I can put them in this remaining 2k minus n orbitals in this many ways. So, these are the number of ways that I can pick an electron, this is the number of ways that I can drop the electron. So, total number of m electron excitation is obtained when I multiply these two quantities. Now, this binomial coefficients n m is given as this n factorial divided by m factorial multiplied by n minus m factorial. So, that you can evaluate this for a few example system. If I continue to do this, suppose I have got this n number of electrons. So, suppose I want to excite all n electrons and find out the entire number of total number of Slater determinants that I can construct, that would come out as this binomial coefficient of 2kn, the C2kn. So, this is the total number of Slater determinants that are possible after I complete my Hartree-Fock calculation. Hartree-Fock wave function is only one such n electron wave function that I have used. Now, there is much more, many more n electron wave functions given by these Slater determinants that can be used as molecular wave functions. Now, we have got a large number of basis molecular wave functions to start with, and now we will discuss how we can utilize this to improve our Hartree-Fock method. One such idea, which is very simple in its concept, although quite hard in its implementation, is what is called as configuration interaction. So, one Slater determinant, we also call this as a configuration. This is one configuration. If I excite an electron, a single excited determinant is another configuration. Then now the third one is yet another configuration. So, now when I was doing Hartree-Fock calculation, I was restricted with only one configuration. I was not allowing this configuration to interact with other possible configurations. Now, what I am going to do with configuration interaction is allow an interaction between one configuration, that is one Slater determinant, with another Slater determinants, which are anyway two different n electron wave function for my molecular system. Now, the configuration interaction approach tells that the total wave function, the final wave function, that is the wave function from CI formalism, this is configuration interaction, short for CI. This psi CI can be represented as a linear combination of all these 2k n combination number of Slater determinants. So, I have one term, that is the Hartree-Fock, that is the ground, the first Slater determinant that I constructed, that is the Hartree-Fock determinant. Then all 1 electron excitation terms, all 2 electron excitation term, all 3 electron excitation term, and I can go on until all n tuply excited determinants. So, this sum will go until n tuply excited, that means singly, doubly, triply, as and up to whatever number of electrons you have in your system, you can go up to that. Now, alternatively, instead of looking at these individual terms, just to simplify the writing, we are calling that this is the original one, the ground wave function. This is all singly excited terms, these are all doubly excited terms, these are all triply excited terms. So, the total wave function is now being expressed as a linear combination of many such n electron wave functions. Some are singly excited, some are doubly excited, some are triply excited. So, all these wave functions. Now, this sounds like a linear variational problem, because our wave function is being expressed as a linear combination of all these functions. The functions we already know, because once we know the spin orbitals, we already know this, we can construct these Slater determinants. The functions we know. What we do not know are these coefficients. So these coefficients and thereby the corresponding energies can be obtained by a linear variational principle. So the idea is that we will evaluate this energy of the CI formalism by calculating this expectation value and essentially solving the set of secular equation. So to do this, we would construct this so called CI matrix. So this is again a general formulation. So what you see is in the CI matrix, the elements are the Hartree-Fock wave function, the Slater determinant. This is a singly excited, this represents all singly excited Slater determinants. These are all doubly excited Slater determinants. These are all triply excited Slater determinants. So this is a symbolic representation. The real dimension of this CI matrix will be based on how many singles, how many doubles, how many triples you have. But this just is for simple representation. Now, given that we already know the wave functions, we can calculate the energy integrals the way we did for other linear variational problems. So here we have the first term that we see. This is nothing but the Hartree-Fock energy. So this is our starting point, right? Now you see this term gives me the matrix element of this Hamiltonian with Hartree-Fock wave function and the singly excited, and this term says the matrix element of the Hamiltonian from Hartree-Fock wave function and doubly excited and then triply excited. So these are the functions are now all Slater determinants. In few classes earlier, we learned how we can evaluate the matrix element of one electron operator and two electron operator when the wave function is given as Slater determinants, but that time we are only evaluating the expectation values. Bra and Kate had the same Slater determinant. Now you see that the Bra and Kate have different Slater determinants. They differ from each other in number of electrons, which spin orbitals are occupied. So therefore, we have to use some set of different rules that known as the Condon-Slater rules to find out what are the values of these integrals. Some of these integrals are going to be 0, some of them will survive. Based on that, we construct a large CI matrix, diagonalize them, obtain the eigenvalues. Those eigenvalues would be, the lowest of them would be the ground state energy, all other will be the excited state energy, since it is a variational problem. So we would, let us say we focus only at the ground state energy, and that ground state energy would be the CI energy, right? But before we come to this the energy part, let us consider that, let us say if I have 10 electrons, I have to consider 10 electron excited determinants. So I am going to get many such determinants. So if I take all n electron excitation and do a full CI, that means I go up to the capital N number of excited Slater determinants are considered. So that will be called full CI. Practically speaking, except for few systems, we cannot do full CI. If the system has maximum 2 electrons, the full CI is simply doubly excitation. If it has three electrons, then full CI is up to singly, double and triple excitation. But if n is much larger, then you can imagine the full CI is going to be very difficult. So often what one does is that uses a truncated CI method, either by considering only the doubly excitations or the single and double excitation. So they are called DCI or doubly excited CI or single double CI. So no matter whether you are doing full CI or truncated CI, at the end you will have a large CI matrix that you will diagonalize. The lowest energy would represent the ground state energy, and that energy, when you compare that energy, call that ECI, that CI energy, when you compare the Hartree-Fock energy, you would see the difference that we obtain from the Hartree-Fock energy. That particular energy is called as the correlation energy. Of course, this has slight, it may be a slight misnomer, because we already know that there are some correlation already present in Hartree-Fock energy, but it is conventionally accepted that we call this Hartree-Fock energy as uncorrelated and uncorrelated energy, and all other energy contributions that are coming from the post Hartree-Fock method, configuration interaction being one such, all this extra energy that we are obtaining are called the correlation energy. So this way we improve upon the Hartree-Fock energy by doing a configuration interaction calculation. Now So we learned, so far we knew that we have these basis functions. When we use larger basis functions, our calculations would become better. But if we consider only Hartree-Fock as the procedure, in that case we are only considering one Slater determinant. But now we have realized that actually there are many n electron wave function. In fact, this combination 2k n number of Slater determinants are possible, but Hartree-Fock calculation does work with only one such Slater determinant. Now, as long as you are working with one Slater determinant, even if you take the best basis function, still you can only approach a particular to an extent, but you cannot go beyond. That limit is called the so-called Hartree-Fock limit. But now we know that there is another dimension along which we can progress, and that direction, suppose I do this for a particular only for a given value of k basis functions, and naturally I will keep my k low and take all the Slater determinants that are possible. Of course, number of Slater determinants are going to rise significantly when I have large k, so therefore I am going to do it for a small k. But in case I am considering small basis function and considering all the Slater determinants, I am actually going to full Ci limit. But that also is not the full truth. The exact solution, the exact answer lies somewhere in between. So we have to make progress on both the dimension. We have to take larger basis functions as well as multiple Slater determinants. So this path would lead us to get exact result. As long as we are staying in this path, the calculations are called well balanced calculations. Otherwise, suppose if we take great basis functions but no electron correlation, so that is a biased one, or the other way around, we take very weak poor basis function but consider many Slater determinants and do Ci, so that also is not a well balanced calculation. A well balanced calculation would make good progress both in terms of basis function and Slater determinants. Of course, you cannot have everything at once because it involves huge computational cost. Depending on your computational budget, one decides how to do. So Ci, configuration interaction, is one approach to extract the correlation energy that is missing in Hartree-Fock method. There exists yet another class of methods where one uses perturbation theory to extract this correlation. How do we use perturbation theory? We have already seen that in case of perturbation theory, we start from a known zeroth order Hamiltonian and see what is the perturbation. Now, in this case, the full Hamiltonian is the molecular Hamiltonian, which has one electron operator and two electron operators. And the true solution would have given us the wave function psi and the true energy E. But what have we done with Hartree-Fock is essentially sum of several one electron Fock operators, so FIs. So each Fock operator is having a core Hamiltonian plus this effective one electron interaction, where the other electrons have been described as some kind of charge cloud. So you have Coulomb interaction, we have exchange interaction. Together, this Coulomb and exchange, we call them as the Hartree-Fock potential. So these are the effective potential that an electron I experiences in a molecule. Considering this Hartree-Fock potential, we have solved the Hartree-Fock problem. So the difference from the true molecular Hamiltonian is given over here. The true molecular Hamiltonian would have this real electron-electron interaction. That we have not considered. What we have considered instead of calling them two body interactions, we have considered them as effective one body interactions. So the difference that we have taken here, that what we have achieved and what we ought to achieve, is the perturbation in this case. So this is the perturbation that if we can incorporate in our system and do a perturbation theory, because we know how to do this perturbation theory, in that case we can extract electron correlation that is missing from Hartree-Fock method. So of course we know how to do this perturbation calculation and get first order energy correction or second order energy correction. So for perturbation calculations, we require a set of unperturbed wave functions. So in this case, what are the unperturbed wave function? They are simply all the Slater determinants that we can have after Hartree-Fock calculation. So they would represent the unperturbed system, and the Hamiltonian H prime that we see here is the perturbation Hamiltonian, and using them we can extract first order, second order and higher order energy correction. It so happens that the first order energy correction does not contribute anything to on top of the Hartree-Fock energy. So, the lowest order perturbation theory that contributes to energy correction is the second. So, that is why this method, the perturbation treatment, goes by this name Moeller-Plesset perturbation theory of the second order, because the lowest order energy correction that appears is the second order. So, but in general, since we already know perturbation formalism, once we know the basis unperturbed basis functions and the perturbation Hamiltonian, the procedure can be pretty straightforward. All right. So, apart from these methods, there are like the configuration interaction and perturbation theory, they represent two different ways, two different directions as to how to extract electron correlation in a system. Apart from this, there are other methods, for example, multi-configuration SCF method, where one uses more than one configurations to start doing this electron excitation that we did with in CI formalism. In that case, we took only one Hartree-Fock wave function and did electron excitation. So, that was a single configuration. We can construct many different configurations and do similar excitation from all the different initial configurations. That would give rise to the so called multi-configuration SCF method or MCSCF method. These are very important techniques when one looks at systems with electronic degeneracy and excited state spectroscopy. So, their multi-configuration SCF methods are very useful. The other important class of methods are the so called coupled cluster method. So, they have rather a lot of similarities with CI. It's essentially collecting different configurations and doing an interaction between them. But in coupled cluster method, there is a slightly different way as to how you collect these configurations and extract your correlation energy. Either multi-configuration or coupled cluster method, both of them are called wave functional calculation, because you start from this Hartree-Fock wave function and then the spin orbitals, and they are your starting point to go ahead and do your electronic correlation calculations. But apart from these wave functional methods that we discussed, like let us say Hartree-Fock, CI, MP2, MCSCF or coupled cluster, there exists a different class of methods. They go by the name density functional methods. So, as opposed to wave function methods, their primary feature is their primary starting point is the density of the system, and density functional theory requires a different starting point. So, this is beyond the scope of our course, but this is one of the most popular methods that we use, and using density functional methods one can actually go and treat many large systems in biomolecules, materials and so on and so forth. So, but this requires a different theoretical formulation that lies beyond us. So, in this lecture what we looked at is that while we discussed Hartree-Fock theory with great rigor, we discussed all the details of Hartree-Fock theory, Hartree-Fock formulation, but we also must realize that there are quantum chemical methods, approximate quantum chemical methods that lie beyond Hartree-Fock theory. But for most of these methods, Hartree-Fock theory or the Hartree-Fock wave function acts as the starting point. You build upon the electron correlation from the with Hartree-Fock method as the starting point. So, in this way we can in future classes, in future courses, we would learn about other better electron correlation method or the post Hartree-Fock methods. Thank you for your attention.